Hello, everybody. We are going to continue the topic of the basic concepts that we want to cover before we start talking about the mass balance in for reactive systems, and we're going to talk about a very important point, which I'd like to start with this question, which is: do reactions proceed to completion? By completion, mean that the reaction continues until all the limiting reactant is consumed. And to answer this question, there is a very important point that needs to be clarified in the beginning, which is the difference between performing the reaction in a lab and performing the reaction in industry or in a real process for producing a product to make profit. So if we are performing the reaction in the lab, then we are doing the reaction to study something about the reaction, either the rate of reaction, the effect of the parameters on the reaction, the temperature, pressure, whatever the conditions that we want to test. And in these cases, we do the reaction in on a small scale in test tube or in a beaker, flask, whatever the system that we have. And in this case, we can easily control the conditions of pressure, of temperature, and we have the freedom of time, meaning that I can do the reaction on in one day, in a few hours, in 2 days, 3 hours, whatever the time frame that we want. It's fine, as long as we are achieving the goal. On the other hand, if we are doing this in an industrial scale, things tend to have a different perspective, meaning that we are looking at the reaction from an economical point of view. That this is a reaction that produces a product that will be sold and we will make profit out of this. So it has to be a feasible process, meaning that I have to make sure that the profit that I make is more than the expenses that I pay. So we don't have the luxury that we have in the lab when we do the reaction in an industrial scale. So I don't have the freedom to keep the reaction going for days in order to convert all the limiting reactant, because this will cost a lot of money for the conditions of the reaction, for heating, for adjusting the pressure, for the equipment size. There are many things that will be affected by this. So in many cases, and I would say most of the cases, we sacrifice part of the reactant because we want to make the process feasible. So I can be okay with converting, let's say, 60-70% of the limiting reactant instead of converting 100% of the limiting reactant, because the profit that I'm going to make from converting the extra 40% would be less than the expense of converting them. So this is an important thing. So that's why in some cases we don't let the reaction proceed to completion for economical and practical reasons. Because sometimes the reaction is very slow, so I don't have time to let it go till it completes. And even if it's not slow, when the reaction proceeds, the reactants become less. The number of moles of the reactant become less because they're consumed. So their concentration decreases, and so the rate of reaction decreases as well. So even if the reaction is quick in the beginning, it gets very slow at the end. So it takes a lot of time until these small amounts left are totally consumed. So we design the reactor to convert part of the reactants, and then we separate the unreacted components and recycle them. So this is one reason. The second reason is something that is not within our control. It's for practical reason, for the nature of the reaction. Some reactions are, and many reactions are reversible, meaning that the reactants produce products and the products produce the reactants again. So there is no way the reactants will be totally consumed. So for these reasons, the reactions don't go to completion, and for these reasons, we define this new factor, which is the fractional conversion. So the fractional conversion is a term that indicates how far the reaction goes, and it's calculated as follows: the number of moles reacted divided by the number of moles in the feed. And the number of moles reacted is the difference between the feed minus the product. And for example, for the same example that we discussed before, if sulfur oxide dioxide reacts with oxygen to produce sulfur dioxide, then we have, let's say, 100 gram moles of SO2 and 45 gram moles of oxygen. In this case, oxygen is the limiting reactant. And let's say what reacts is only 80 gram moles, which will react with 40 gram moles of oxygen, producing 80 gram moles of SO3. So the product would be 20 of SO2, moles of SO2, 5 moles of oxygen, and 80 moles of SO3. So in this case, not all the sulfur oxide reacted, not all the oxygen reacted, and that's why we have some more oxygen and SO2 with SO3 in the product. And in this case, if we want to calculate the fractional conversion of, let's say, SO2, then it's going to be the moles fed, which is 100, minus moles out, which is 20. So it's the moles reacted, which is this 80 moles, divided by the moles fed, which is 100. And the same for oxygen, it's 45 minus 5 divided by 45. So this is the conversion. It's going to be 0.8 and 0.888. Of course, conversion, the fractional conversion is dimensionless because it's a ratio between moles and moles, so it is dimensionless. And it's important to note that the fractional conversion is not the same for all the components. It can be the same under only one condition, which is having the feed component or the components fed with the same stoichiometric ratios. So if it's 50, then it's going to be 0.8. And if you multiply them by 100, it's going to be percentage. So it's going to be 80% and 88.8%. So it's exactly like the mole fraction and mole percent, like what we did before. So this is what we use to describe the how far the reaction went. And we can look at the fractional conversion as a way of describing how far we are from the ideal case. Ideally, all the limiting reactant should be consumed, but actually what happens is that it's not totally consumed. So this fractional conversion tells us how close we are to the ideal case. We can put it this way. This is what reacted compared to what should have reacted if the reaction goes to completion. So this is the definition of the fractional conversion. So let's look at this example here. We have acetylene reacting with hydrogen, and we know that producing ethane, and we know that we have 20 kilogram moles of acetylene, 50 kilogram moles of hydrogen, 50 kilomoles of ethane are charged into the reactor. So we have some of the product fit to the reactor with the reactant. And we need to know what would be the product if the product contains 30 or if 30 kilogram moles of hydrogen has reacted. So what we can do is we write the reaction, make sure that the reaction is balanced, and then we write the feed 20, 50, and 50, and we can write the numbers. So I know that 30 kilogram moles of hydrogen are reacted, which correspond or should react with 15 kilogram moles because the ratio is 1 to 2 to 1, and will produce 50 kilogram moles of or kilomoles of ethane, and then the product would be 20 minus 15 consumed, it will be 5 kilomoles. 50 minus 30 is 20. 50 minus 15 is 65 kilomoles. So these are the number of moles that we have. And if we want to calculate the conversion of acetylene, it's going to be 15 divided by 20. This is going to be 30 divided by 15 for 50 for hydrogen. There's also one thing that's important here to know about the fractional conversion, that it is only for reactants. We cannot do the fractional conversion calculations for the products. There is nothing like this. There is no fractional conversion for ethane. The fractional conversion is for only the reactants. Right, so there is one more parameter that is important, which is the extent of reaction. I'm going to keep it to the next video. So I'll see you then, inshallah. Goodbye.